Good afternoon, everyone. I'm Matthew Winook, the project manager for the hardware and embedded systems team, and I'm going to tell you a little bit about the Hydras project. Many of you might know the SDSU Mechatronics Club, a group of student engineers, excellent student engineers who developed an autonomous submarine for an international robo-sub competition. The competition consists of 7 events that the sub has to traverse. One of those events that every team struggles with year after year is the passive sonar navigation event, and that's where my team comes in. SDSU Mechatronics has sponsored us to develop a system that can determine the direction of arrival of signal coming from pingers. The event consists of 2 active acoustic pingers programmed to produce short bursts of sine waves. The 2 pingers produce 2 different frequencies, and to add complexity to the event, the pool is broken up into the practice and the event side. Pingers on both sides are active at the same time. Yeah. So, as I said, every team year after year struggles with this event, and being the overachievers we are, we developed 2 solutions. One solution we developed is the time of arrival. It is a system that literally tracks the time it takes for the acoustic wave to travel from one hydrophone to another. The other solution we came up with was to capture samples of the sine wave and post-process it to determine the phase shift. These solutions essentially give you the same information but require drastically different circuitry. Additionally, the 2 solutions benefit from different hydrophone geometries. So we developed a hydrophone mount that will accommodate this with close proximity for the phase shift solution and a larger spacing for the time of arrival solution. Now I'm going to pass this over to Tony, who's going to talk a little bit more in detail about the time of arrival solution.
Thank you, Matt. Hello, everybody. My name is Tony. I'm a member of the software team for Hydras. So here's a closer look at the 3D printed mounts that we have. As Matt mentioned, we have 2 different solutions for this problem. And there's 2 reasons we went about doing this, because for the first part, we wanted to make sure that during the day of during the competition, we wanted to ensure that this system worked, because it's worth a lot of points, and many other teams struggle with this. And so the first reason we decided to go with 2 solutions is for redundancy. If for whatever reason one system were to fail or produce erratic results on the day of the competition, the sub could just rely on the second as a backup. The second reason we wanted to do 2 solutions is for solution confidence. If both of these independent systems are producing the same result, the same angle to the pinger, then that's a really good indicator that it's a good solution. Or, say one solution is telling us the pinger's off to the left somewhere, and the other solution is saying the pinger's off to the right. The sub's computer can then ignore that as an externality and wait for a later ping to hopefully produce the 2 solutions that agree with one another. Now, to go into more about the time delay of arrival method, if you see the pinger off to the side here, you see the distance to one of the hydrophones is going to be longer than the distance to the other. And we can actually measure this difference in length by sampling the 2 hydrophones. Basically, we're looking for that high pressure wavefront to incident at each of the hydrophones, and we're counting the number of samples that the microcontroller samples at in order to figure out how long of a period in time the difference took. And that, along with the speed of sound in water, will give us this length. We already know the spacings of the hydrophones, and so then it's just a simple matter of some trig to get the angle to the pinger. Now, for the phase shift solution, I'm going to pass it over to Mikey. He's going to talk about the DSP.
Thank you, Tony. Hi, everybody. My name is Mikkel, and I was on the software team. Now, for our phase shift method, we consulted with Fred Harris because he showed us a way that you can use DSP to solve this problem. Now, what the DSP or the method essentially does is this is the raw data that we get from the hydrophone. So here's the RoboSub, it's rotating. Here's a pinger, or a hydrophone. Here's the pinger emitting the wave. These are the signals that we measure. Now, what Fred's method does is it takes the signal and heterodynes it. So in other words, makes it a complex signal which looks like a phasor. And then with the phasor, it's really easy to measure the phase angle using the arctangent. And then using that phase, we can find the bearing. So right now, when the two complex signals are aligned, we're pointed directly at the target, which is what you just saw there. So basically uses a Hilbert transform to make a complex signal and a lot of DSP magic, and that's how it works. So with that, I'm going to pass it over to Marianne, who's going to give a software overview.
Hi, my name is Marianne, and I'm the project manager for the software team, and our task was to develop a graphical user interface, or GUI, for the sonar system. So our GUI consists of many different components, and these components consist of textual data, like a console that shows us the position of where the pinger is when it emits the frequency in the water and what angle we need to tell the sub to go to, as well as it allows us to actually set the frequency, because at the competition, they tell us the day of what frequency that we need to detect of the pinger. So we were able to provide the textual data for the team, and then we also presented them with visual representations of the data. So when the hydrophones read in the data, we're able to reconstruct it into the two different solutions that the other guys talked about earlier, the time of arrival and the phase shift. And so when developing a software, it's important to split it up, the task, into different phases, like the initial phase and the final phase, which is what we did. So during our beginning phase, we were trying to get serial communication working, because we need our software to be able to talk with the PIC microcontrollers that the hardware team programmed, and then with that, we need to tell the main computer on the sub where it needs to go. So once we got the serial communication working, we tried to make the data parsing as efficient as possible, and we wanted to create the graph. So we used simulators while the hardware team was developing their PCB boards to kind of give us a test environment so that we could see that our software actually worked for when they actually implemented their microcontroller PCB boards. So once they were finished with that, we were able to integrate our software with their solutions, and we integrated all the components together to complete the GUI, which you will see later on, and I'll pass it on now to Jessica to show you more of our simulator.
Hi, I'm Jessica. I'm with the software team. So before we were able to implement the serial communication, the time of arrival, and the phase shift solutions into a working GUI, we first created test simulators to get plotting working with the communications and our calculations. So this simulator shows a moving sub, and from this we're able to calculate the distance and angle of the sub relative to the pinger, display that in the console below, and use that data to update the sonar graph to the right, which uses the angle calculation to determine if the pinger is to the left or right of the sub. This next simulator shows data from all 4 hydrophones, and these sliders on the left allow us to adjust the phase delay between each for the time of arrival solution, and that data is then sent through serial communication to another GUI, which then updates and plots. So now I'll pass it to Cody, who will show you how it all came together.
Thank you. What's going on, guys? My name is Cody, and I'm part of the software team. Now, they've already told you about this mystical GUI we have. Well, there it is. It's right there. Now the next question would be, why? Well, simply put, it's for tuning, validating, and verifying what we're doing. It's not used during the competition. I know some people have had questions about that, but it's used before the competition and possibly after, so we can tune it. We can fine-tune any of the stuff we want. For example, up here at the top, we have some text boxes that we can send information to the embedded side. The hardware side needs to know what frequency they're looking for, the threshold to trigger some of their values off of, and spacing of the hydrophones, for example. If we were ever to change that design, we can simply say it right there without having to bust out the code and look through thousands of lines of code there. Favorite one here are the graphs. Now those are interchangeable. Right now we do have 4 that are pretty important. This one here is the bearing. It's going to tell us left or right, where the pinger is left or right. This one here is going to tell us the angle of inclination, so the depth-wise, where the pinger is. This one here is a very important one. That's the FFT. That's DSP for Mikey, that's showing us the frequency of any of the signals we're reading in. Now here, this is easy because we're only getting one signal, but we're going to get noise possibly in the water, seagulls, crying babies, whatever it is. There's going to be noise. And we're going to be able to see that here, overlay it, and then pick clearly 25 kilohertz, which is our target frequency at the top of the box there. Now that's that. So again, it's a tuning tool. I'll pass you off to Tony for communications.
Okay, so as mentioned, these two systems, the time of arrival system and the phase shift system, are completely independent. So they both need their own means to talk to the computer. And we're doing this over serial communication using RS-232. And so for the phase shift solution, the DS PIC is the microcontroller handling that. It's sampling the 4 hydrophones and sending that whole data package over in one big chunk. And so the computer can actually reconstruct the signal in real time for each ping. For the PIC, for the time delay of arrival, we're using the PIC24 as the microcontroller, and all that's doing is measuring the time interval between the incident waves on the 2 hydrophones. And so now to go over a little bit more about the hardware overview, I'm going to pass it to Charles.
Hi, my name is Charles Washburn. I'm the assistant project manager for the hardware side. So to recap a little bit on what Matt was saying, one of the main goals of our project was to design a system that can determine the bearing for a target pinger relative to a sub. And so how does the hardware help us achieve that goal? So I want to take the complex design that we have, take a step back and give a big picture overview of our system and attempt to give a broad and simple explanation on how it works. So up here I have the block diagram of our hardware system. It's located on a circuit board which plugs into the back plane of the robo sub. In other words, it plugs directly into the computer of the sub. Again, we have 2 solutions, a phase shift solution and a time of arrival solution, which are broken out on the board. So let's go ahead and talk about the phase shift solution with the hardware involved. Down here, if you can see, we have a target pinger and we have 4 hydrophones. This pinger is going to send off a signal. It's going to hit 1 to 4 of our hydrophones. The hydrophones are going to send these signals off to the hardware, and the hardware is going to filter out the data and signals that we don't want, clean up the signals we do want, and send that off to the computer. And then it's going to be nicely packaged to where the software can then reconstruct analog signals so that, again, like Tony was explaining, or excuse me, Mikhail was explaining, that we can get the phase difference between them and therefore calculate the bearing. Now for the time of arrival solution, again, our hardware will only be receiving signals from 2 hydrophones, and then our hardware will be able to determine the number of samples between the signal arrival at each hydrophone. And then with the number of samples divided by the sample rate, we'll then be able to determine the time difference of arrival of that signal at each hydrophone. Now I'm going to pass it on to Alan Williams, who's going to discuss more about the phase shift solution.
Hi, I'm Alan. I'm from the hardware team, and one of the things I worked on this semester was the signal conditioning for the phase shift solution. As Chucky just mentioned, we went with the DS PIC for the phase shift solution in order to use the 4 ADCs that it has. But in order to do that, we need to first do 3 things to the incoming signal from the hydrophones. First of all, the signal for the hydrophones has a maximum of 8.5 volts peak to peak, but the DS PIC microcontroller operates on 3.3 volts. So we need to attenuate that 8.5 volt peak to peak signal down to less than 3.3 volts. And next we need to use a DC offset to level shift that signal to where it exists between 0 and